All right. Great. Thanks very much, Munzer, for the invitation to be here and for the nice introduction. Yeah, as a non-Game of Thrones viewer, I was glad you were able to keep that in terminology. So, okay. So, audio is okay? Everyone here? Great. Okay. Yeah. Well, it's great to be here, and I was at the whole first day yesterday, and just the talks were obviously fascinating, as all of you saw, and really very nicely illustrates the strength of IDSS, the combination of areas which has been obviously talked about in many of the talks, and also just this overriding question of how can we use all this to really try to make society better, right? To try to identify problems in the world and use this combination of tools to actually provide insights that might be lacking at the moment. And so, as I look at the program for today, there's a whole set of other exciting things that I think are going to try to address some of those issues in these other areas. I want to start actually with something that, in a way, harks back to the very interesting panel that happened early afternoon yesterday, talking about the online world, the world of online social systems and what's been happening with them. I'm going to talk about sort of two snapshots from the recent work we've been doing on this. One with Jason Gaetani and Eva Tardosh, one with Sendhil Mullainathan and Manish Raghavan. All five of us at different times and different configurations have had both Cornell and MIT affiliations, since Jason will be coming here as a postdoc very soon. When I was thinking about this work, I was actually thought back to a talk I gave here as part of another celebratory IDSS event early in IDS's history, September 2016, another very interesting conference, which was happening in the midst of a contentious presidential election, as you may recall. One of the other speakers was Nate Silver, and the audience was looking for him for reassurance that the 2016 election would turn out okay. I was talking about social media, and already at that point it was clear that in order to understand online social media systems, you need to understand the social systems in which they were embedded. And I was showing pictures like this, how political mobilization takes place on social media, how we get much of our information, through that one degree of separation that we have to people in social media. What is the role of the ambient social system? And so, but also to be sort of keenly aware of the risks that arise in these situations, and as you saw in the panel yesterday. And actually, at that conference, I was reminded of another conference that I was at during another contentious presidential election in 2004, Bush versus Kerry, where I actually had the good fortune to meet Elihu Katz, the person on the left, who, with his mentor Paul Lazarsfeld, the two of them were two of the founders of the theory of mass communication in the middle of the 20th century. Right, and had a huge influence on our thinking about how broadcast communication, how TV and radio operate. And we compared notes in 2004 because he was thinking back to his own conference during a contentious presidential election in 1948 and 52, where they were looking at the disruptive effect of technological change on the political process, radio and TV. And what they found, and they wrote about in several books, in this book, Personal Influence, for example, is that radio and print media, for that matter, seem to have only negligible effects on actual vote decision. When people were asked what had contributed to their decision, their answer was other people. Right? This is 1955, looking at disruptive technological change in the middle of the 20th century. And so the point they were making, though they didn't phrase it this way, is that at some level, all media is social media. Right? The Paul Lazarsfeld's two-step flow theory says media reaches people, and then the people disseminate it to many other people. And we do this sort of effortlessly, right? We think socially about media so easily that we often don't even realize the ways in which our brain maps this, right? So to pick one screenshot from the lead up to the 2016 presidential election, when this IDSS conference was held, this was in the spring when the Democratic primary was going on. So Rolling Stone's endorsement here was for a Democratic candidate for president. It was not in the general election. And they endorsed Hillary Clinton in March 2016. And Matt Taibbi, who at the time was a sometime writer for Rolling Stone, was unhappy with this endorsement. And a millennial apparently had some brilliant cutting reply to Matt Taibbi's displeasure. And this was recorded in a headline in thepeoplesview.net, some blog that I have never read before or since. It popped up on social media. And But I screenshot it because there was something about this sentence that kind of struck me as, it seems to encapsulate the social nature of online media in an important way. Because think how large a cast of characters are in this sentence, right? This is not a sentence about Hillary Clinton or even Rolling Stone's endorsement of Hillary Clinton. It's sort of about Matt Taibbi's displeasure, but not even that. It's really about a millennial who has a brilliant response to Matt Taibbi's displeasure. Of course, you're not hearing from the millennial. You're reading thepeoplesview.net. So your brain somehow maps these at least 5 characters in this. Now, your brains are doing something even more complicated because you're not reading thepeoplesview.net, right? You're at least 2 more degrees of indirection away from this. And so the point is, right, our opinions get carried through sometimes many chains of links, and sometimes they're in reaction to, sometimes they're supported by, all of this. And so the question, that you might want to ask yourself is, if all media is social media, then what's actually special about what we call social media, right? Online media. And you could argue that really what distinguishes it, of course, is modern social media is algorithmic media, right? That what's genuinely new here is the extent of algorithmic mediation and platform optimization that's taking place when we do this. And the point is, it's somehow crucial, really, to think about the feedback loops that exist between the human behavior and the algorithms. And then that third component, what the impact is on social outcomes. Social outcomes at the collective scale, but also social outcomes even at the individual and dyadic scales. And obviously, with these algorithmic feedback loops, there are these increasing concerns about algorithmic amplification leading to conflict. And again, that was the subject of this very interesting panel yesterday. And it sort of, plays out in a lot of different recent areas, right? The whole idea that after 2016, people really, I think, appreciated in ways they hadn't before. Maybe they knew they should have, but hadn't fully appreciated, that we need to approach social media like we approach all algorithms in a risk framework as well as an opportunity framework, right? We need the risk framing on this to say, what are the possible failure modes? What are the possible adversarial attacks that can take place on these systems? How do things go wrong, potentially in emergent ways that we didn't expect, right? And so a lot of interesting work, both theoretical and empirical, right? It really runs this full spectrum, looking at polarization, looking at misinformation, the possibility of radicalization pathways set up by algorithms, and the possibility of outright adversarial attacks, right? Just as you get adversarial attacks on other kinds of computer systems, that's something that we see in social media as well. So with that in mind, I wanted to tell you sort of 2 snapshots from within this risk framework of thinking about social media. The 2 snapshots here are actually going to be theoretical. In both cases, they actually come from some really extended conversations that my co-authors and I have had with some of the largest social media platforms, where they're really trying to come at these problems, both conceptually and also really down at the systems level. But I'll talk more at the theoretical level here, because in some sense, I think one reason that it's been hard to talk about these things is we lack some of the modeling language that we have in many of the other aspects, right? When we started with social media, we had a lot of modeling language for talking about things like link prediction, for things like trend detection. And we didn't necessarily have a corresponding modeling language for some of these risks. And so this is to try maybe backfilling some of that language. And so in that sense, my 2 vignettes will be sort of more mathematical. Actually, in this talk, the math comes slightly early. So the first one, I'll talk about a model that Eva Tardos, Jason Gaetandi, and I looked at for how adversaries might target social networks with the idea of changing opinions. And then in the second one, I'll talk more about things that happen at the more individual level. Okay, so the first one. So if I want to think about adversaries and how they might target a social network and how that might shift opinions, then I want some model of how opinions respond to external forces. And one of the models in the mathematical sociology that's been most useful for this, and the one that's in some sense been by far subject to the most empirical investigation, is this thing called the Friedkin-Johnson model. Right? So this has been used, originally formulated by Noah Friedkin in the setting of small group lab experiments, subsequently used to study opinion shifts in elections in India, in bilateral country negotiations in the Paris Climate Accords. In a sense, it's a very simple model that imagines a collection of nodes. We'll think of them as people. They could be other entities. And we're going to imagine that rather than each node simply expressing, say, an opinion in a one-dimensional spectrum, each node actually has an internal opinion, right? So these three nodes form opinions about something that can be sort of organized one-dimensionally. Think political spectrum if you want, or think, assigning levels of belief to something. And so their internal opinions are in these squares. They're 0, 1/2, and 1. And then each node faces the problem of expressing an opinion. And because of the social interaction component, you derive value from being true to your internal opinion, but you also derive value from not disagreeing with your neighbors, right? Those are the two forces that you're trying to balance. And so the Friedkin-Johnson model, and there are many potential extensions of it, but let's just stick to the simple one, is that the expressed opinion at each node you'll update to be a weighted average of your internal opinion SI, right? So your revealed opinion ZI is average of internal opinion SI, and the average opinion of your neighbors. Okay, so in this case, the one on the left would say 1/4 so that it can be an average between its own 0 and the half that's being expressed by the one in the middle. Right, the one in the middle is sort of tugged in both directions, so it has the good fortune to be able to express an opinion that's actually its own opinion. But that's sort of from the symmetry of it. Now, whenever I have an averaging problem, I could say, well, this is also, the average is the optimum of a quadratic function. So I could say equivalently that, if they're computing the average, we could have imagined this to be them solving an optimization problem, that I have to select a ZI to minimize the squared sum of distances from my internal opinion and from all my neighbors' opinions. Because if I'm minimizing the squared sum, I'm going to use the average. And then if I think about that optimization problem and I ask, where would all this averaging lead? It would lead to an equilibrium where I have globally optimized this function. And so if I set derivatives to 0, what's interesting is that the Laplacian matrix of the graph sort of just pops out automatically. Because if I just sort of gather up all the coefficients, there's kind of a weight for every one I have a neighbor to, and then I have, a term for myself each time, so I have the degree showing up. And then I also have a 1 from my own internal opinion. So if I set derivatives to 0, I get the Laplacian plus the identity, which just says I also want to match my own opinion, times z is equal to s. That's just saying derivatives to 0. And so we get this formula, which is z has this nice closed form relationship to s. And that's why, in some sense, the Friedkin-Johnson model is sort of analytically a nice thing and why it's been sort of empirically studied as much as it has. OK. Now, let me tell you a scenario involving adversarial intervention. So the scenario is that an adversary would like to perturb the internal opinions so that a lot of disagreement happens. Right? So an adversary targeting a network to create disagreement. So imagine the world starts in this happy state where everybody's internal opinion is 0, and so of course they all express 0. And an adversary is able to come in and perturb these internal opinions up to some total budget of R. They can go and push this one a little positive, this one a little negative. They can do whatever they want. They like to maximize disagreement. Now, disagreement, let's just say, is the sum of the squared differences across every edge. And so that's a quadratic form. So I could just write the disagreement as Z transpose LZ, and I would actually get this back. And we already have our closed form for what Z is, so I get a larger closed form for in terms of S, right? The original internal opinions is this quadratic form in terms of the Laplacian matrix of the graph, right? That's what the adversary is trying to do. So it's really a very clean description of how the adversary is attacking the graph. And now we'd like to maximize that quadratic form. Okay, so you want to maximize the quadratic form, you'd like to align your vector, your perturbation, with the eigenvector for the largest eigenvalue here. Now, these matrices, the Laplacian, I plus L inverse, this larger matrix, or this more complicated matrix, these all have the same eigenvectors. They just have different eigenvalues, right? They're simultaneously diagonalizable. And in particular, this matrix is essentially L over 1 plus L squared, so its eigenvectors are lambda over 1 plus lambda squared. So if you want to pick the eigenvector that is going to be the best disruption to the network, you want to find this sort of weak seam in the network, and it's going to be the one that's aligned with the eigenvalue that maximizes this. Now, the eigenvalue that maximizes this is not the one that maximizes it in the Laplacian. It's the one that maximizes that expression. That expression looks like this, right? So you take the eigenvalues of the Laplacian, you sort them here, and you find the one that's highest up on this x over 1 plus x squared curve. Right? You find the one that's closest to the peak, which is at 1. And so what's interesting is that the adversaries, right? So this is sort of the first thing that Jason, Ava, and I found looking at this model, that the adversary is trying to attack the network along a kind of middle eigenvector, right? Like, we spend a lot of time thinking about the second eigenvector or the top eigenvector for the Laplacian. But here, somehow the adversary is going to pick an eigenvector between one sort of arbitrarily in the middle, depending which one ends up closest to this peak. And it's even sort of more interesting in a way, because let's imagine one final thing. Let's imagine I have a knob, and I can tune the strengths of the edges connecting people. Right? So imagine I put one parameter alpha here on the edge weights. Right? Now the edge weights tell me how much I'm averaging opinions with my neighbors. Right? So my own belief, I want to be consistent to that. That has a coefficient of 1. But to my neighbors, I have this alpha times wij. So as alpha goes very high, I'm doing a lot of averaging. I care about my neighbors. As alpha goes very low, I'm doing very little averaging. I care about my internal opinion. And what does that imply about how the adversary should attack the network? Well, these eigenvalues all scale with alpha. So, right, so when alpha is, up here, they're all off to the right. Right? And these red things are almost like sort of beads on a wire that I'm like sliding up and then sliding down, right? As alpha changes, they slide to the top, they slide all the way down like that. And so the point is, as alpha ranges over all possible values, the adversary's strategy changes, but it changes in this funny way. It does not change smoothly. It actually changes in this kind of ratcheted way where it just moves from one eigenvector to another as alpha changes. Alpha changes smoothly, and the adversary's strategy goes over n different things, the n eigenvectors of the graph, right? So this turns out to be an optimization problem that doesn't just involve the largest or smallest eigenvector. It involves literally every eigenvector of the graph as I parameterize it. And in a way, it's intuitive. Because the case of large alpha means the adversary is thinking about small eigenvalues. Right? Now, small eigenvalues govern the behavior of large cuts. Right? So the case of large alpha, the adversary should be looking for sparse cuts. Whereas in the case of large eigenvalues, right, they govern the behavior of max cuts, as made famous by Michel Gomans, who's with us this morning. And so the case of small alpha, large eigenvalues cover that. And so this is actually intuitive in a way, right? Because for large alpha, the adversary is attacking the graph, trying to create disruption. But large alpha means there's a lot of averaging going on. So what they want is to create as little averaging as possible. So they would like to do this blue cut, where the two groups become basically opposed polarized factions, right? And there's very little averaging that can happen, even though alpha is large. When alpha is small, very little averaging is happening. So what the adversary wants to do is bring two groups with enormous surface area into contact, because since they don't average away their opinions, that conflict will remain. Right? And that's effectively something that looks like a max cut, but in some sense a spectral max cut. Okay? And the point is, in between, I have less intuition for what's going on, right? Like I don't have a succinct explanation to you for why the adversary fills in each of the other n-2 eigenvectors, except that in between, they're trying to find some optimal balance of creating disruption in the presence of different levels of averaging out of these opinions. Okay? But so this is sort of, in a way, the sort of key point, right? A point that emerges from this Friedkin-Johnson model that's certainly very true about real social media as well. The same network is doing two things, right? That network is how you get your opinions and how you update your opinions. It's also how you measure your interpersonal conflict with people. Both of those are happening on the same network at the same time. And that's what's so subtle about these sort of, not just adversarial attacks, but the way polarization can arise. And one of the interesting things that you can extend this model to look at, which I won't talk about here, is to ask what happens as our interpersonal networks become increasingly divergent from the networks on which we get information. Right? This is yet another way to think about a point that came up on the panel yesterday, that as we encounter information online from strangers, but we have genuine fights with the people we see every day in our lives, it's a sort of divergence between two networks. Right? Here it's the same network. But eventually the network on which I'm receiving information may be different from the network on which I'm having conflict, and to ask about how that actually, what implications that might have. Okay, so that was the first vignette I wanted to tell you about, and that's really about trying to create some sort of language for thinking about adversarial attacks on networks. And it turns out that there are potentially interesting things that one can say, and we're now bringing this back to some of the data that people have used to look at the Friedkin-Johnson model in the past to see how this might look. Okay. Let me go back to my original slide here, right? Lots of work on this idea of conflict and risk that arises from social media. But I want to talk about one other kind of risk. And this came about when Manish Raghavan, who's now here as an assistant professor in College of Computing and Sloan, and Senthil Mullainathan, who I've been a behavioral economist I've been working with for a long time. The three of us were thinking about some of these issues. We were talking to people at some of the largest social media platforms, and we realized it's one other kind of conflict that's going on that's really important if we want to understand the dynamics of how people are using social media. And that's not any of these. It's really how it creates conflicts within yourself, right? That it's not only you're having conflicts with other people on social media, you're having a recurring conflict that's taking place entirely inside you, right? What do I mean by that? Do you believe me that social media leads to conflicts within yourself? Well, I guess my argument is the fact that we have to invent a word called doom scrolling means that there's a part of you that somehow can't seem to go to sleep at night because you keep reading about all these horrendous things that are going on in the world. Another part of you that would like to put down the device and go to sleep and not think about this, right? The fact that people joke about themselves being professional internet quitters who are ready to offer advice, or the fact that some people can ingenuously ask on Reddit, how do I spend less time on YouTube? When the answer at some level feels like it ought to be obvious, right? Suggests that there's something going on where, right, there's genuine conflict. And so this has been the subject of an increasing amount of work in the empirical behavioral sciences over the last 5-6 years. With interesting studies such as, for example, the Alcott Gensko song study, showing that if you incentivize people to get off of social media, they report, in the same spirit of like the kind of habit formation work that we heard about in Esther's talk yesterday and others, that eventually that habit can stick and people can actually report higher levels of happiness, right? So there's some other diagram here that there's a split within you, right? There's a part of you that wants to use Facebook, a part of you that wants to override the part of you that wants to use Facebook. Now, how should we think about this kind of conflict? And for this, the fact that Manish and I are working with Senthil, who has a long history of thinking about behavioral biases, right, as a behavioral economist by training, Senthil observed that, the correct dichotomy here is the dichotomy between want and should, right? That the want-should conflict shows up in many kinds of goods where there's a risk of overconsumption, right? So, for example, if you want a quick summary of want versus should, it would be this, right? At the break, perhaps, or at the lunch today at the conference, perhaps they will offer potato chips and salad. And part of you will, want the salad, and part of you will think you should have the potato chips. Closer to us, maybe is the idea of like want versus should in media consumption, right? We are talking about media consumption after all. And that happens too, right? You're on a plane, there are 2.5 hours before you land, you're thinking about movies you could watch. Part of you wants to watch the Avengers movie, but part of you thinks, I really should watch this educational documentary about the font Helvetica. I'd become very well educated, I would learn a lot, it would help my future conversations. I should do that. They actually seem to get this, because the subtitle, the little instructions here say, start watching with your public library card or university login, because they somehow know deep down that the only people who might possibly watch this have either a public library card or a university login. And so these are the kinds of conflicts that, and both of these conflicts have been studied empirically, in the offline world. They're related to time and consistency, right? They're related to the thing you want to do now, one other part of you believes they're going to regret having made that choice later, right? So there's a sort of different time scales going on here. And there's a lot of empirical work going back at least 10, 15 years now that people consume want goods in the more immediate term and should goods over the longer term. So just to pick my two domains here, food and media consumption, this group of behavioral economists, Katie Milkman, Todd Rogers, Max Bazerman, right, for example, did work with online grocery orders, showing that if you looked at how far out, right, with a manual labeling of items in the grocery store, which it's a finite problem, you can label them, looked at, online grocery orders contain more should items when they're placed to be received further in the future, whereas things to be received now have more want items. The mail order DVD era, similarly, right, so you may remember, those of you old enough to remember that Netflix was once a mail order company. You asked for DVDs to arrive in the mail, and then they came, and you watched them, and then you mailed them back, and you got new ones. And they found that when there was a FIFO violation in your Netflix queue, in other words, you ordered A, then you ordered B, but then you returned B before A, meaning B showed up and it jumped the queue and you watched it, under a manual labeling of movies, because again, there aren't that many movies made by major studios, so we can manually label them. B is more often a want movie, A is a should movie. Actually, this had an interesting reflection even in the Netflix prize competition. So some of you may remember the Netflix prize competition from right around this era, actually, 2009, which is, well known in both the recommender systems community and the privacy community. And the funny thing about the Netflix prize competition is, right, this $1 million prize to improve Netflix's recommendation. They gave people data. They could work on the data. All of that data came from the mail order era. All of that data was an answer to the question, what do I think I'm going to watch 3 days from now? Or what do I aspirationally want to commit my 3 days from now self to watching? People trained classifiers on this. And then right as that competition ended, Netflix, for inevitable business reasons, moved to the streaming world. And all of its data looked completely different. Its data was an answer to a completely different question, which is what do I want to watch right now with the press of a button? Right? And so the whole nature of preferences changed. Right? Same people, but you offer them a different question on a different time scale, and then preferences change. So there are several sets of preferences bundled away inside you. It's not that one is right? It's not that wanting the chips is wrong and wanting the salad is right. It's that you have two genuinely conflicting sets of preferences. Now, why is this a problem? Well, because, of course, Netflix and every other online platform has to answer the question, what do users want? And the fundamental principle of user modeling, right, so fundamental we tend not to articulate it, except occasionally, is revealed preference. Right? People choose what they want, so choice reveals preference. Right? The whole power of digital traces for using online platforms is that we have just, at this point, trillions of mouse clicks, and they all reveal choices. And we're going to try to infer preferences. But if your preferences, if you have more than one set of preferences, and they're in conflict, then we have a communication problem. Right? We have whatever other problems we've already talked about with social media, but we have one more problem. Right? Even if I got to build the platform, right? I get to build a Chrome browser extension that's going to help me manage my consumption choices. It's working for me. There's still a communication bottleneck between me and the Chrome extension because I have these two dueling sets of preferences, and they're all being expressed through a single channel of clicks. How do I know which is which, right? Now, this is not to say that revealed preference is right or whether it's wrong. You could actually argue that it really is a question about we need to understand the media we have to understand how to use the revealed preference assumption. Right? It may be that my choices for salad are different from my choices for chips. Right? So, for example, my co-author, Sendel, who really thinks this paper as sort of entirely about his obsession with Doritos and how he can't stop eating them, talks about how, he's at a party and there's a bowl of Doritos and he, of course, eats all of them. And, the host sees the bowl is empty. And half of Sendel wishes that, the host is going to come out with another bowl, and half of Sendel wishes the host will take it back in the kitchen and not bring it out again. But the problem with the social media platform is it will always refill the bowl of chips because it's giving you what you clicked on. Right? And that may make sense for salad. It may not make sense for chips. So that was the question we were asking ourselves. And so let me tell you about a simple model that we built. Right? This was an area where we really, if you go back to the time and consistency literature, right? So David Labeson's work on hyperbolic discounting, Ted O'Donohue and Matt Rabin, right? My colleague at Cornell, some of their work on time and consistency. That sort of gives us some language, but we sort of need a new model for the idea of doing this for media consumption. And so let me tell you about the simplest model that we worked with. There are more complicated ones also, but in the simplest one, let's just think about a linear feed. Okay, so the user's consuming a linear content feed. So think Twitter timeline, YouTube playlist, Facebook newsfeed, TikTok, right? So items t equals 0, 1, 2. So really just a single decision. Do I continue the next item or do I stop? And again, we have these warring preferences going on. So we'll say the user has two sets of preferences. I'll call them system 1 and system 2. Now system 1 and system 2 are these sort of two characters who show up in a lot of behavioral economics, right? Sort of, again, made famous by Danny Kahneman. And they get used for lots of things, right? Heuristic problem solving versus analytical problem solving. We're using a particular meaning of this metaphor here, which is simply system 1, in the context of preferences, acts impulsively and acts first and does not plan. System 2 is slower to act. It only acts when system 1 is disengaged, and it's capable of planning. And we'll think about system 2's utility, right? So in our story, the main character will be system 2, right? It's the part of you that looks reflectively back at your session on social media and decides whether they regret or are happy with what happened. Okay, so here's our model. I'll tell you the simplest version of the model so that we can have some math that we can digest in real time here in this talk. There are more elaborate versions also that we've looked at. So item T right? T equals 0, 1, 2. The whole question is just, do I keep scrolling or do I stop? It produces some utility U sub t for system 1. Let's talk about system 1. Drawn from some known distribution. Now, because system 2 does not plan, and it only just decides, do I want to grab the next chip, we really only care whether ut is positive or negative. If it's positive, then, and we'll say this positive with probability p. So this is some arbitrary distribution, but the mass to the right of 0 is p. And if so, system 1 just continues on to item t plus 1 because it's engaged. It got positive utility. If ut is less than or equal to 0, something more interesting happens. System 1 gets bored and temporarily powers down and hands control to system 2. Now, what does system 2 do? Well, system 2 is capable of planning, so it has a slightly more complicated problem. Item t also gives system 2 some utility. Let's call it v sub t. Right? So system 1 gets u sub t, system 2 gets v sub t. These are not necessarily opposed to each other. Right? It's entirely possible to have something that's both very engaging to system 1 and also valuable. Right? There's nothing wrong with that. But they might also be misaligned. Right? It's just a different distribution. So it's drawn IID from v with mean v bar. And there's some outside option for leaving the site and, like getting on with the rest of your life. And we'll call that w. So the net utility from item t is vt minus w. And the point is, system 2 is planning. It knows these distributions. So it knows the distribution of future items, but doesn't know their actual realizations. Now, if this were the whole thing, and vt, so this is only interesting, I guess, if v bar is bigger than w, so that there's some reason to keep going. But in that case, why wouldn't system 2 just stay here forever? Right? System 2 should just stay on the site forever if v bar is bigger than w, because it's going to get positive utility every time it's in control, in expectation. So we need one last thing, which is satiation. Right? Eventually, system 2 is going to have diminishing marginal returns for this. It's going to satiate on the content. Now, there are a bunch of ways to model satiation. The one that's easiest to do here in real time in this talk is to imagine that satiation takes place as a random on-off transition. But you can imagine much more gradual forms of satiation, and the model can handle those too. But let's do this one because we'll be able to do calculations in our heads. Let's imagine that what's going on is every step, a coin gets flipped with probability q. And when it comes up tails, system 2 decides, I'm now done. I'm no longer getting value from this content. I would like to leave. Okay? So that's the idea. So, and system 2 knows this. So probabilistically, it knows that the probability it's still going to be interested t steps from now is q to the t. Right? And this simple model is memoryless, although more complicated models obviously are going to have memory. All right. So 3 key properties of the content. And I would argue they really are 3 axes along which we can describe online content. Right? One is the value that you get from it. Right? This v bar minus w, the net utility per item. A second one is the satiation, or the span of the content, right? The time span of the content. The probability q that system 2 remains interested per item. And finally, borrowing this word from the behavioral economics of food consumption, the moorishness, right? How much system 1 wants more of the thing. So the probability p that system 1 is in control when it consumes a piece of content. Right? And again, I would argue that in our conversations with some of the teams working on these social media things, we've been thinking about, like, this is an interesting sort of 3-dimensional classification of content, right? The value, the satiation, and the moorishness. Let's ask what system 2's planning problem looks like in this setup. Right? I've now told you a model. And so let's imagine that system 2 controls the decision to go on the platform in the first place. Okay? We'll come back to that assumption. That's a self-interesting question. What is the problem it faces? Well, you can sort of analyze, because I've made the model very simple, but it has the behaviors that sort of the more complicated models have also. You can actually just analyze in this one slide. Right? The user session can be viewed as having 2 phases. Right? I mean, the session is whatever it is, but analytically, us as the analyst of it can imagine 2 phases. In the first phase is when system 2 wants to continue. During this phase, in blue, it's collecting v bar minus w utility per step. And we're just waiting for a coin to come up tails. So the expected number of steps in phase 1 is 1 over 1 minus q. And so its expected utility is just this. Now phase 2, system 2 decides it would like to leave. Does it get to leave? No, because system 1 might be engaged. Right? It's sort of like system 1 and system 2 went to a party, and system 2 would like to go home, but system 1 is still talking to people, and system 2 can't somehow drag them out. So while phase 2 is going on, system 2 is collecting minus w net utility per step, because they're getting 0 value and they're losing this outside option. How long does this last? Well, it lasts until system 1 next gets disengaged. That's also waiting for a coin to come up tails. This is 1 over 1 minus p. But of course, there's a chance that it ends immediately, that the first coin's tails, so it's really p over 1 minus p. Okay, and so that's the second term. Now, in a deterministic model of satiation, which is surely a kind of potentially more reasonable one, we'd have to do some infinite sums, and you get basically the same answer that you get from this very clean thing. Right here, in a sense, we're sort of piggybacking on the heuristic that we know how to compute this geometric sum and figure out this expected value. But it's not harder to do the deterministic satiation. Deterministic satiation introduces one more ingredient that this one doesn't have. Because it's not memoryless, you'll see behavior where system 2 actually often leaves early, right? Because they know that this content is so engaging that although they're still enjoying themselves, they rationally decide to step out early because the next time they're going to be in control, they will have burned away all of that utility. Okay? But here it's memoryless and a bit simpler. So the utility is actually just this random variable with this very simple looking expectation. It has two terms, right? The first is v bar minus w1 minus q, and then minus pw1 minus p. Okay, now the point is, let's consider the data that the platform, or for that matter, your browser extension that's helping you manage your time. What is the data that they have? They have your time with regard to the site, right? Time on site. Let's call that your engagement with the content. And your engagement is just session length, and it's a random variable with this, 1 over 1 minus q for phase 1, p over 1 minus p for phase 2. And so we have this pair of equations. Utility is here, engagement is here. And they both have two terms. They both are 1 over 1 minus p and 1 over 1 minus q. One of them agrees in their sign, one of them disagrees in their sign. And that, in a sense, is exactly this internal conflict, right? That mixed sign is exactly the internal conflict. Because long sessions means at least one of these two terms is big. But it matters a lot which of these two terms is big. If this one's big, then long sessions mean you're getting utility. And if the second term is big, it means long sessions means you're wasting your time and burning away a lot of utility. Right? So this is the broken communication channel that we have. If we can just observe how long you're there, we can't tell why that is large. Right? If p equals 0, right? So in a world where we're not thinking about this conflict, that world is a special case of our model. It's the case p equals 0. System 1 just never boots up. And in that world, we see why engagement is a great proxy for utility. The longer you're there, your utility is growing monotonically in the time you're there. But if p might come from a large range, then maybe there's a large value of p. And if p actually gets large enough, the user might decide not to visit the platform at all. Let me actually jump ahead to show you just one little calculation we can do with this, and then I'll wrap up. Imagine a platform. And imagine a platform that's even trying to help you maximize your utility. Or maybe a platform that's just trying to maximize your time on site, right? They might have different objectives, right? They might be cynically just keeping you there as long as they can. They might be trying to actually create a good experience for you. Either way, they have the following problem, right? Imagine, in my simple example, that they know how to parameterize their content, right? So that they can sort of mix together a playlist for you. And in this very simple example, let's imagine they have a one-dimensional parameter x, which turns out to control p, right? Then they aren't quite sure what this x does. It's a knob they can turn. And they notice that as they turn the knob, you're on the site for longer and longer and longer, right? But unbeknownst to them, as they turn up x, your utility is going down, down, down. And eventually, x gets so large that your utility drops below 0. And system 2 rationally decides just not to come back to the platform. Right? So there's this interesting paradoxical thing that's actually recognizable from engineering practice on these platforms, that at the moment the user seems most engaged, often they just sort of go cold turkey, and they never come back, right? Because it's reached the point where the user says, this is just way too much a waste of my time, I have to stop using this platform. Right? And that's exactly this discontinuity that you get to as you keep driving this parameter up. Right? You don't necessarily see the cliff coming unless you're sort of attuned to this issue. Okay, so that's the second example of a risk with social media. This one taking place entirely internally within the user, right? And so all of this really sort of starts from the sense that something isn't working with platform optimization, right? We all have this intuition that platforms keep optimizing, and the more they optimize, the less happy you are. And it's sort of useful to have a modeling language to talk about why that might be happening, right? What might be going on here? What are some parameters we might be trying to collect? I think what's interesting in this second vignette is some of the ways this helps us reason about the design choices that we make in social media, right? So what are some examples? One is this point that I've been sort of stressing throughout, which is how to interpret the data we collect, right? The fact that you have warring preferences going on inside you, and yet we're collecting a single stream of data. The role of surveys. Obviously, clicks are not literally the only thing that these platforms see, right? So when a survey pops up that says, how are you enjoying YouTube today? Or did you get out of Facebook what you wanted to when you came on the platform today? Right? This is essentially a platform, knowing that there's this communication breakdown and trying to reach out and talk to System 2 directly. Right? Answering that survey is a System 2 activity. System 1 is not interested in answering surveys, and so maybe that's them talking to System 2. But think about how many orders of magnitude separate the rate at which you click on content and the rate at which you answer surveys. Right? Even under the most optimistic view of participation in surveys, you're several orders of magnitude apart in the amount of data you can collect. Right? So we have this incredibly fine-grained view of System 1 and a much coarser view of System 2. I talked about a linear feed, but of course, you can also take a branching version of this model. Right? I'm not going down an infinite path of content. I'm going down an infinite tree of content. At every step, I have options ahead of me, and I have to decide which one to pick. And there are interesting results there, which obviously I won't be able to get into here, that there's some intermediate optimum in how many options. Right? If I start increasing the number of options, I have more chance to increase my utility. But too far, and there's just way too high a probability that System 1 is engaged. Some other interesting things, the benefits of enforced breaks. So both Instagram and TikTok within the last year have announced a new feature that you can configure in your profile to force a break every half hour or every time. Now, if you only cared about keeping the user on the platform, right, why would you possibly advertise as a feature that I'm going to force you to sit there for 30 seconds doing nothing? And the answer is because if you appreciate this System 1, System 2 conflict, guaranteeing the user that they will always have the ability to leave every half hour might be what pushes them sort of from this part where they're over the cliff back into an area where they're still actually deriving utility. Finally, last point, this question about who controls the decision to go on the platform is also actually one that brings in interesting, subtle design choices, right? So we said System 2 decides to go on the platform. It's a planning activity. We can debate that, right? You opening your phone when you're standing in line, and looking at social media is sort of somewhere perilously on the balance, and small things can tilt that balance. Right? So you can imagine, for example, saying that I normally read the Washington Post, but not Sunday mornings. So on Sunday mornings, they embed clips from YouTube from Saturday Night Live the night before, and I don't go on YouTube. But when I'm reading the Washington Post, suddenly this clip appears in the middle of a news article, and I'm already watching YouTube, something I was trying not to do. Right? An idea that right, and so the design choice has actually tilted the delicate balance between System 1 and System 2. Something that we behavioral scientists know from the psychology of food consumption, right? That you vary your route through the airport so as not to go by the place that sells the cinnamon rolls that are 1,000 calories each because you don't want to stop and buy one. But the cinnamon roll place knows that also, so they pipe the smell of the cinnamon rolls out into the concourse. So as you're walking through the concourse, you're already eating the cinnamon roll, right? And so again, these design choices, we can interpret many of them as sort of aiming at, there's a delicate balance that you yourself negotiate between System 1 and System 2. You use commitment devices, use your own behavioral strategies, and design choices can sort of either help that or they can disrupt that. And these are, again, things that we can think about and things that potentially come into play when we have a language for doing this. So the hope here was to sort of think about these last few years of social media, the risk kind of framework that we can bring to it, right? The idea that there are risks at all these, both in the conflicts that we have with each other, and the conflicts that we have internally within ourselves. And then if we can try developing a language for talking about all these things, it might help inform some of the design choices that we're all going to need to make going forward. Thanks very much.
We have time for questions.
Hi.
So I know this is a model, it's a beginning. Thank you. So you broke this down into the second part into these two, System 1 and System 2, which you could view as short-term thinking versus long-term thinking, which then opens it up to actually there being a continuum.
Yeah.
Can you comment on that?
Yeah, so that's something that we've thought about, right? So this is a very simple version where I have these sort of, right, I have something which is in the immediate present and something which sort of looks out for arbitrary long terms. Yeah, so you can think about a few things. For example, I mean, one that seems maybe needlessly complicated but kind of interesting is like, it's not clear there are only two systems. I could create sort of a partially ordered set of systems where, one hands-off control to another one, each has different timescales. Yeah, but more generally, this is really about the timescales over which I'm planning, right? And one is in the immediate present, and so it discounts the future with discount factor 0. It just nothing. The future doesn't exist. And the other one has some discounting of the future. You can imagine that like I have sort of the systems are characterized by different discounting rates, or even, for example, each time I draw some draw from a discounting rate and work with that. And you can sort of see that it's sort of an echo of the way in which, for example, the time and consistency literature in behavioral economics, looks at both kind of continuous functional forms like full hyperbolic discounting, which is often analytically more hard, versus, say, quasi-hyperbolic discounting, which in a sense is the modeling decision to sort of recognize sort of two timescales, the present and the non-present. So I think looking at those kinds of interpolations is definitely very interesting, yeah.
So take the perspective of recommendation system engineers now. So it seems that, okay, the theory, some structural model, you could probably fit a structural model in the near future if you wanted to do that. One fundamental limitation here seems to be which proxies do you even use?
Yeah.
So if you really only can observe clicks, what do you really do? And isn't there a fundamental limitation in which kind of world of eliciting user feedback we got in, where it seems to be just so much to ask a user for how do you really feel?
Yeah, it's a great question. So actually this, right, so I think one other interesting thing that one could do, which I didn't have a chance to talk about here on this conclusion slide. So this nice work of Smith and Milley, Luca Belli, and Moritz Hart, which talks about sort of these other kinds of like silent actions users take that are sort of signs that like system 2 might be speaking, right? So for example, the decision to mute another user or to mute a piece of content, the decision to click don't show me this again, the decision to downvote, these are all things that are presumably system 2 because they're all about you doing something so that your future self gets some better experience. And so looking for those as they get sprinkled into a session. Now, any one person does those rarely. But to come back to your point about recommendation systems, obviously any one user does everything rarely. And so now we can leverage that across other things. There's also other kind of, sort of natural shocks to the system. So for example, one thing we've talked about with the people working on these is like app crashes are kind of interesting, right? The app just crashes. Do you come back and restart your session? If not, I learned something maybe about how the session was going in the sort of immediate run-up to the app crash. But anyway, so all of these are sort of things that like, each of them are rare, but again, then we can sort of integrate over all the people experiencing them, yeah.
Hi. So after seeing your research, I'm worried because so it seems like system 2 is what keeps us healthy and sane. And I read some research on addiction, which says when people are addicted to something, they literally cannot think long term. So the longest they can plan for is just a couple of days out. They cannot think what happens years into the future. I'm trying to think about what do you, so basically are there things that prevents social media companies deteriorating our system 2 thinking, getting us addicted to the platform, and keep continuing this kind of business profit model? And so on?
Yeah, it's a great question. Right. So one question is like, how does this relate to the political economy of like large platforms and their business models, the system they operate in? I think that this is a fascinating question, which there's sort of a few things to think about. So one, the platform is not your only intermediation to the content, right? And again, I think we're seeing an increasing number of client-side extensions, client-side applications that you can try deploying to actually regulate your consumption of things. So in some sense, these kind of things could be tools on the platform side. They can also be tools on the side of the user. So that's certainly one thing that I think is certainly relevant. A second is that we can sort of think of these platforms as operating on a continuum, right? Like, large platforms include, YouTube and TikTok. They include Wikipedia. They include, Khan Academy, they include Stack Overflow. Each of these comes with their own, right? So in a sense, the question of like which ones are addictive, which ones have addictive content is sort of operating on this continuum where we typically don't think of Khan Academy as addictive, we don't think of Wikipedia as addictive, but in some sense it's operating on similar design principles to these other platforms. So I think one thing that's useful is also to sort of take into account the entire design space because it gives us worked examples all along the spectrum of like how different strategies are playing out. And I think obviously in other areas where there's overconsumption, behavioral economics has come in with ideas of how do I food has an overconsumption problem, tobacco has an overconsumption problem, alcohol, gambling, right? And in all of these cases, we think about, how do we do behavioral interventions, both behavioral interventions informally, but also, how does that inform regulation, for example? And all of that has historically begun with models of the phenomenon at work, right? So, the work on overconsumption of tobacco, for example, had a lot of detailed modeling of how that operates. And so I think in these cases, having some understanding of what's going on so that, on the side of people who have all the concerns you're mentioning, we have the ability to offer advice on what the steps might be that best mitigate this.